even though there's obviously not enough time for everybody who's here to give a long talk at the meeting, we wanted to make sure that everybody who has something exciting to share has a little bit of time to share it. The purpose of giving a 3-minute talk is obviously not 3 minutes. Is obviously not to explain everything in great detail. It's simply to advertise, here's some really cool stuff so that those of you who hear this can go up at the next break or at the next beach encounter and find out all about this wonderful stuff. So it's basically showcasing cool ideas. So without further ado, I'll let you take off here, and I'll give you a 2-minute warning, a 1-minute warning, and then I'll just come intimidatingly close. Take this mic here, and you're off.
Okay, thank you. I'm going to be talking about advertising a work I did answering this question. How rapidly can a short-shell black hole be destroyed? How rapidly can you start with a short-shell black hole and end up with no black hole, just matter in empty space? And there's an easy way to do it, which is to wait, but that's very slow. A black hole evaporates in a time m cubed, which for a solar mass black hole comes to 10 to the 57 times the current age of the universe. You might wonder whether this process can be expedited. Classically, it can't, but there's in fact a proposal going back to the early 80s saying that you can mine a black hole and destroy it in a time that scales like m, a much more rapid time for a solar mass black hole, a time that goes like a few milliseconds. And my talk is going to be saying that that's wrong, that in fact you can only mine a black hole in a time m cubed. There's a fundamental lower bound on the lifetime of the black hole. The proposal was this, that you go very close to a black hole with a box that's the black hole surrounded with Hawking radiation. You lower the box in, close the box, and drag the Hawking radiation out to infinity. That literally is the proposal, and it doesn't work. And the reason it doesn't work is because of the null energy condition. It's actually a mechanical engineering constraint imposed by the most permissive energy condition we know about. There it goes. The problem is that the tensile strength to weight to mass per unit length of any material, including the rope that you're trying to build it out of and the box that you're trying to build it out of, is bounded by the laws of physics. So if you're trying to build a space elevator, I mean, this is essentially a space elevator you're trying to build near a black hole. If you're trying to build a space elevator, the essential material science property you're interested in is getting a rope that is very strong but very light because it has to support its own weight. But that's bounded by the null energy condition. It's bounded by this quantity that's 1 in natural units, or 10 to the 17 newtons per kilogram per meter in SI units. And that basically makes this impossible. 1 minute. If you try and use any material that doesn't saturate this bound, then you end up having to make the space elevator very much thicker at the top than at the bottom. In fact, so much thicker at the top than at the bottom that either the bottom is so light that a single Hawking quantum breaks it, or the top is so thick, of the rope is so thick, that the whole rope undergoes gravitational collapse and forms a black hole of its own. Whereas if you use something that actually saturates that, that's the best thing you can do, like a fundamental string that saturates this, the rope ends up using all of its strength to support its own weight and has none left over to drag out a box. That's it.
Extra applause for finishing 9 seconds early. Next up is David Finkelstein.
I think of nature as the original computer. Space-time is its address system. The field variables are its memory. The action principles governs a distributed processor. In the philosophy of Laplace, the user has to be outside the universe, and she inputs the initial fields and reads out the final fields. And what I'm looking for is the quantum analog. Sometimes they affectionately call it QNIVAC. UNIVAC was one of the first computers I worked on. And now the user is in the universe. Every experiment with input and output is a computation. It's just we don't exactly know what's going on. And my current model, QNIVAC, is quantum both in the cell addresses and the cell contents. The cells have odd Fermi-Dirac statistics. The memory is binary. The addresses are hyperbinary, which I'll explain in just a moment. The cells, the whole system is relativistically invariant. And of course, it's cellular. And perhaps the important thing is that it's modular, and that part of the computer vocabulary is the ability to use cells as vertices of larger cells to go up the level of aggregation. I have to correct my original suggestion. In the space-time code, I thought that the memory of the natural computer was a lot of spins. If you take spin in a sufficiently general sense, that's still right. But I realize now, something that Feynman said long ago, spins are really part of the addresses, not part of the memory. The memory are the fermion occupation numbers, which are binary. And the main contact with reality is that if you look at the hyperbinary code, you get dimensions 1, 2, 4, 16, and this happened to fit the decomposition of the 16 fundamental fermions of the standard model. Thank you.
Wonderful. Thank you. Steve, please come on up.
Okay, there's just time to give basic ideas or make inflammatory comments. So as we discussed yesterday, if quantum mechanics governs nature, then quantum information is conserved, and therefore information must transfer out of an evaporating or disintegrating black hole, or something crazier must happen. I won't go there. This is already crazy enough because it would be prohibited by locality, and specifically the prescription against superluminal transfer of information in local quantum field theory. And so that's telling us that apparently we must find a new foundational framework for physics. And the question is, what is that, and how do we properly describe black hole behavior? So let me give you just a picture of that and say a few words. So again, the idea is information must somehow transfer out of a black hole. And the proposal is that can happen without drastic effects on infalling observers, that it should be nonviolent. This is in contrast to some of the things that have been said recently in a lot of controversy in this story of firewalls. So a few points about that evolution. As mentioned, it must violate locality with respect to the semi-classical geometry. One can give an effective description of it within sort of effective field theory terms by adding new interactions. And I think ultimately a fundamental way of looking at this might be to treat, to replace the structure of field theory with a structure involving fundamental quantum subsystems. And then finally, this story of firewalls, making another, a potentially inflammatory statement, follows from basically making some bad assumptions. So I'll let you just briefly stare at that picture where we have quantum information that you might throw into a black hole, or entanglement, which builds up with the interior of a black hole through the Hawking process. And then ultimately the picture is through some modification of local quantum field theory in semi-classical spacetime, you have an effective slow and fairly innocuous transfer of information out of the black hole. 1 minute, okay, and one slide. Another proposal is that, just elaborating on what I said, the correct fundamental way of looking at these things is based on networked quantum subsystems, and that you might be able to formulate generalization or a quantum version of a manifold by using localization involving subsystems, a subfactor structure, instead of the usual notions of localization and locality in local quantum field theory. And then, of course, such a framework ultimately needs to obey a correspondence principle and match onto the semi-classical story of gravity and local quantum field theory propagating in semi-classical geometry. So those are just some ideas, and I'll just finish with some references and by saying that I'd be happy to tell you more, but that's all I can tell you now. Thank you.
Thank you so much.
Hi. It's been suggested, including by a number of people in the audience, that the universe in some sense behaves like an enormous computer of some sort. And so I'll present a result which gives a unique perspective on this idea. The result comes from the area of complex networks, which seeks to model complexity in the form of a graph. This is a picture of the internet at the autonomous system level. The nodes in this graph are organizations, and the edges represent formal relationships to transmit data between these organizations. Two properties of this graph which are important to consider are the degree of a node, the number of neighbors that it has, and the clustering coefficient, which is the fraction of neighbors of a node which are neighbors with each other. So it turns out that a number of complex networks from different areas, so for example the internet or the brain or metabolic networks, have some common properties. One is that they exhibit a power law degree distribution with a power of around -2, and they exhibit strongest possible clustering given the degree distribution. So there's an effective model for generating these networks which have these properties, which arises from considering a geometric embedding into a hyperbolic space. So this is a finite portion of the Poincare disk. We consider a Poisson process, which gives a collection of points in this disk. And then we connect a pair of points if their distance in the hyperbolic geometry is less than the radius of the disk. So this defines a random process which gives rise to a network which has the desired properties, a power law degree distribution and strong clustering. The coordinates in this model have a interesting significance. So the distance from the center represents the popularity of a node, and the angular coordinate gives some indication of the homophily of the node, so that nearby nodes in the angular space tend to be more likely to connect to each other. So it turns out that you can map this, this model, which is defined in the hyperbolic space, to a space of Lorentzian signature, namely de Sitter spacetime. The mapping is quite simple. It works as follows. The radial coordinate in the hyperbolic plane gets mapped to the time coordinate in the de Sitter, and the angle is preserved. And so it turns out that the disk that I showed earlier gets mapped to the past light cone of a point in the de Sitter spacetime, so that the network arises from the causal structure. And so it turns out that this model, it gives exactly what we want. It gives the power law degree distribution and the strong clustering. And so I'll just close with a very speculative remark that our question, does the universe self-organize to arrive at a geometry which optimizes its ability to act as an information management system? Okay, thank you.
Thank you. Fascinating. And next up, we have Diego Blas. And remember to make little mental notes of all the questions that you want to ask these speakers, so you can continue these fascinating topics over at beach and coffee discussions.
Okay.
I'll give you a 1-minute warning.
Thank you. Okay. Hi. So I'm going to talk about how to derive space-time from space and time. I'm following a bit the idea of making inflammatory remarks. So here is a line of thought which is kind of classical. So you have a special relativity that generates space-time structure and gravitation. Then general relativity kind of follows under quite broad assumptions. If you add quantum mechanics to it, then our best theories of gravitation are kind of complicated, so kind of difficult, and all of those have to address issues which are not totally settled, despite of many years of big effort on those. One thing one can do to try to make things simpler is to challenge the assumptions and at the different levels. So I want to challenge the first assumption. Okay. So I want to see what happens if I have a theory where there is no space-time, but there is something else, and then space-time is emergent. So this is something which is quite a hot topic nowadays. I want to do it in a way which is in a way that I lose the less possible information. So I want to still keep rotations invariant and translational invariant, add gravitation. Then what I have is something close to general relativity plus a preferred time direction. Okay. If I add quantum mechanics to it, it was suggested 5 years ago by Orjava that you can have quantum gravity within a perturbative quantum field theory framework, which is much simpler than any other proposal. We have been spending some time checking that the phenomenology is fine, so there was some confusion at the beginning. But nowadays you can, with the new theories of this time preferred direction, everything is fine. These theories have a lot to say about the different issues of quantum gravity. So for high energy behavior, maybe okay. For black hole thermodynamics, we have new ideas for what non-locality may be. Also for black hole singularities, but I must say that most of that is work in progress. And I won't talk about this today, but, and I forgot to say that we have even a cool name, which is chronometric theory. So there is time, which is chronos, and then metric, so cool name. But what I want to discuss in this minute is, I don't want to hide the controversy about these theories, which is that spatial relativity and space-time is something that has been proved in experiments since 100 years and even more. The smart way to make these theories alive is to try to make this space-time as emergent property of our experiments at low energies. And what my message today is that this possibility happens, and it happens, I put here two possibilities. Let me just discuss the second one. It happens due to quantum effects. So in this plot, I show the difference in, let's say, in the propagation of different species. And it happens that if this difference is big at short distances, it tends, just by quantum polarization, it tends to be small at short scales. So this calculation you can do in perturbative quantum field theory, and this running is logarithmic. What we are doing now, we are trying to do it in non-perturbative quantum field theory. So we are trying to use ideas from lattice or ADS-CFT, and ultimately from quantum simulators. Thank you.
Great. Thank you very much. Wonderful. And last up in this lightning session, we have Yong-Shi Wu.
I'm going to talk about some recent results of mine with my postdoc and student on exactly soluble models for topological matter. The issue here are the highly entangled states, quantum doubles, and the holography. These are my students. So motivation is that, this topic is related to topological quantum matter, topological quantum field theory, and topological quantum computation. It's really address some prototype physics of quantum information, which may have connection to fundamental physics. So the model I'm talking about here is Len-1 Z2 model, which is due to the so-called Kitaev toric code. So we put the qubits on links of the trivalent graph. The Hamiltonian consists of two terms. One term is the vertices term. Each term here acting on the qubits around a vertex. Then another term is plaquette terms, which acts on the qubits around a plaquette. And the Hamiltonian is designed so that Q's, B's are commute with each other. So the problem is exactly solvable. But however, the key point here is that the eigenstates, which of Hamiltonian actually, they are eigenstates of the Q's and the B's are highly entangled states. A term in condensed matter physics is the so-called tensor product states. On a torus, there's ground state degeneracy. Okay, so we have proof, in certain sense, 3 theorems. First one is that the ground state, especially on torus, is degenerate. These degenerate ground states are classified by topological charge arising from quantum double. Quantum double is a generalization or analog of Lie group and the Lie algebras. They are topological observables related to quantum double. If we consider the so-called plaquette fluxon excitations, again, they are classified by quantum double and topological observables, and also statistics are related to these things. So, then theorem 2 is if we bipart the torus system into 2, a canonical basis of the quantum double, actually in the subspace of a degenerate ground state, give us a set of so-called minimal entangled states. So then here we can see the connection between quantum double and entanglement. Also, topologically, there are 2 distinct ways of biparting the system. Then the overlap matrix of the 2 set of corresponding minimal entangled states actually coincide with the modular S matrix. So modular S matrix also has some interpretation in terms of quantum information. The third one is that in a particular model, we call a lone-one Fibonacci model, in which the entanglement entropy of a bipartite sphere actually can be written as the entropy of a windy system, which is a boundary of the bipart system. So here we can see that we have the holography, especially entanglement entropy of Berg is equivalent to entropy in windy system. So in black hole, we know that there are 2 point view of entropy. One is black hole entropy is Berg entropy. Another one is entanglement entropy. But in this topological model, we can identify the 2. Okay.
Wonderful. Thank you so much.